Welcome to another educational video brought to you by Chrysolite Tutors. This is the part 2 of this course, Unit 3 of Math 105, Mathematics for Management Science, Part 1. You have vectors and complex numbers. In the last video, we looked at complex numbers and vectors, though we'll take off from complex numbers where we stopped. And we're looking at scalar multiplication in complex numbers. Now, when you talk about scalar, you talk about just a number that's not showing anything, not showing direction, but just showing maybe magnitude and maybe the unit, just the magnitude. So if, for instance, you are asked to multiply a constant and or a real number by a complex number, if, for instance, I have k multiplied by a plus bi. This is how it is, where this is the constant, this is the scalar, this is the scalar, and this is the complex number, Here we have the real part and the imaginary part. So for instance, we will say 5 multiplied by 3 plus 2i. This is a simple arithmetic for complex numbers, scalar multiplication. This is the scalar outside. 5 times 3 is 15 plus 5 times 2 is 10i. This is just the answer. So with this kind of arithmetic, we are just to treat it like a simple algebra where the scalar outside multiplies everything inside. Okay, so this is for scalar multiplication. But if you were to multiply complex numbers by another complex number, you know that that's no longer scalar. It's two complex numbers multiplying themselves. For instance, we are to multiply z1 and z2 if or given z1 to be a1 plus b1i and z2 to be a2 plus b2i. Now, if you have something like this, you just represent it. This is I, then 1i, then a2 plus b2i. Agree with me that these two are different things because a1 and a2 are not the same, b1 and b2 are not the same. Okay, so for this one, you just do multiplication by the terms. That's multiply this by this, multiply this by this, then multiply this by this, multiply this by this. So by the first, the line here, you're going to get 4 terms. 4 terms because this is 1, this is 2, this is 3, and this is 4. So let's go. A1 times A2 is A1 A2 plus A1 times B2I is A1 B2I, then plus B1I times A2 is A2 B1I, and B1I times B2I is B1 B2. Now this last one is where the thing is. Remember I told us about powers of complex number in the previous video. You can check out that video if you've not seen it, please. It's pinned in this video. Check it out. I times I is minus 1. Always. This is where you use that thing. I told you, I said, if you have root minus 1, this is I. This is the division of I. Root minus 1 is a complex number, and we use I to define it, or J. Some textbooks use J. So I'm using I for this particular course. So, and if you have, okay, let me put it that way. I is defined as root minus 1, that's the division. Then if I have I squared is equals to minus 1, then I cubed is equals to minus I, and I raised to the power 4 is equals to 1. So just know this. So because we are dealing with I, that's why I'm having minus 1. Okay, so at the end of the day, I have 2 real numbers and 2 complex numbers. So this one can come here, A1, A2 plus B1, B2. This minus, okay, this minus will now make it minus. Please, this minus here will affect the minus in front of it. You understand? It goes, so when I'm taking it to join this one, I'm collecting like terms, I'm taking it to join this one, it becomes just minus b1, b2. So we're done with this last two. So let's go with this second term here, plus a1 b2i plus a2 b1i. Okay, now I can now group. So the real part is a1 a2 minus b1 b2, then plus a1 b2 plus a2 b1, then I. So this is the coefficient of this is the imaginary part, and this is the real part. Imaginary part and the real part. Okay, now if you follow this, is fine. If you follow this like this, is fine. Please just study this what I've done. You apply generally to all problems that are given. But by the time we start solving practical problems, you will really appreciate what I'm doing here. Let me get you some practical examples. So if I have so if I have example, okay, z1 is equals to 3 plus 2i, and z2 is equals to 4 plus 3i. Find z1, z2. So we are multiplying, right? Okay, so we'll bring out the complex numbers. The first one is 3 plus 2i, bracket, close bracket, then 4 plus 3i. Okay, again, I said this one will multiply this, and this one will multiply this. So let's do. So this first one will multiply the 2, one by one. So 3 times 2 is 3 times 4 is 12. 3 times 3 is 9 plus 9i. We're done with the first term. So this one will now multiply this. 2i times 4 is 2 times 4 is 8 plus 8i, and 2i times 3i. 2 times 3 is 6, but I times I is minus 1. Please note this last one. Always note it. It's called minus 1. And this minus will affect this one that is here. So let me go a step further. 12 plus 9i. 9i plus 8i will give me what? Will give me 17i. I've resolved these two. But this one is now minus because of this minus here. Minus 6. Okay, so 12 minus 6 is 6. Then plus 17i. So this is the solution for this particular example. Okay. Okay, so we'll go on to division of complex numbers. So if I have two complex numbers defined as Z1 is defined as A1 plus B1, B1i, and Z2 is equals to A2 plus B1i. Divide this. So what we have now is that Z1 over Z2 is equals to A1 plus B1i over A2 plus B2i. Now, I'm going to introduce what they call the conjugate of denominator. This conjugate is an opposite complex number simply by just putting minus inside of minus operation in between these two terms. Okay, conjugate. So divide. Okay, look at this. Divide both numerator and denominator by the conjugates. The conjugates. Conjugates of the denominator. First of all, what's numerator? Numerator is the fraction up. The upper part of the fractional expression. This is numerator, this is denominator. Now this is denominator now. What is the conjugate? Conjugate is just simply putting the minus operation in between the terms, or changing it to the minus or the plus, as the case may be. If, for instance, I have for this one now, A2 plus B2i, the conjugate is The conjugate is A2 minus B2I. So the conjugate is actually flipping the operation here. Whatever it is here, make it the opposite. You know, have plus minus or minus plus. So if you have minus here as the expression, the conjugate will be a plus. The same terms, but just flip the operation. Operation is this one, this operation. So you have plus, minus, division, multiplication, but we are dealing with only plus and minus. So if you have plus here in the expression, flip it, put a minus and put the term. That's the conjugate. The same thing, but you are changing the sign. If it is a minus that is here, put a plus. So the conjugate of this one is this. So I'm going to multiply both sides by the conjugate. So I'm going to write this one again. I'll say A1 plus B1, then I over A2 plus B2I multiplied by the conjugate of the denominator. A2 plus, sorry, not plus, minus B2I over A2 minus B2I. See what I've done? So I have multiplied both numerator and denominator by the conjugate, okay, of the denominator. So interestingly, what happens what is interesting is what happens at the new denominator. Because what conjugate does is that it makes the denominator without having a complex part. Okay, you will see it now. So I say here, A1 times A2 is A1 A2 minus A1 times B2 is A1 B2 I. Then B1 I times A2 is plus A2 B1 I. Then finally, this and this is minus, yes, minus B1 B2, then minus 1. Please, let me take this off so I want us to really see what I'm doing here. Okay, I'll do it again. A1 times A2 is A1 A2. A1 times minus B2I is minus A1 B2I. B1I times A2 is plus A2 B1I. Then this minus and plus here is already minus, but I have B1, B2, but this II is still minus. So this minus will now sit on to plus. Okay, so we'll just hold this one in your mind. Let us do the denominator. Okay, so A2 times A2 is A2 square. A2 times minus B2 is minus A2 B2I, and A2 B2 is plus A2 B2I. Then what happens here? Now minus plus is still minus, right? But it's B2 square then minus 1. Why? That minus 1 came from I and I. Okay. Now we're using notations to write this. By the time we start using numbers, it will be very clear. Very, very clear. So I said notice what happened here and what happened here. So we're going to take it. So I have A1, A2. Yes. So I have, this is imaginary part. This is real part. This real part, there's a plus here. See, minus will become a plus. So I will take this real part to go and join this side. I will now say plus B1, B2. So this is the real part. This first time and last time, they are the real part. So minus, the imaginary part now is this one. So I have A1, B2 plus A2, B1, then I. The I brought it out from outside. Okay, so all over. Now look at this. This one will cancel this one. Why? Because they are the same thing. The same thing. I have A2 here, I have A2 here, I have B2 here, I have B2 here, I have I here. But there's a minus and there's a plus here. That's what conjugate does. Conjugate will just resolve the denominator to be a real number only. So the complex part has disappeared with this thing now I'm doing. So what I now have left is A2 square. Then minus and minus will give me plus. So I'll say plus B2 square. So this is the answer. That is, we are trying to derive it. You understand? This is the answer. So note what happens. What happens here, first of all, is that when you are doing division of complex number, the denominator, take the conjugate of the denominator and multiply it by both numerator and denominator. You will get a new term. Why are we taking conjugate to multiply? We are taking conjugate of the denominator to multiply so that we can eliminate the complex issue, the complex expression in the denominator. Once you do that, you have invariably made this number a more simplified form. You can actually have a complex form where this denominator will divide this real part, so you have a real component, and this one will divide the complex part, and you have the complex component. So this thing actually effectively is two parts. Let me just conclude like this. Say a1, a2 plus b1, b2 all over this component a2 square plus b2 square. This is the real part. Plus, sorry, no, minus. This is minus. Then a1, b2 plus a2, b1 over a2 square, b2 square, then imaginary part. So we have done that. Okay. So just let us use the real examples, real numbers for us to appreciate this more. So if we have Z1 is equals to 3 plus 2i and Z2 is equals to 4 plus 3i, evaluate Z1 over Z2. So simply 3 plus 2i over 4 plus 3i. Now, what is the conjugate of the denominator? The conjugate is 4 minus 3i. That's it. So we're going to multiply both up and down by the conjugate. So I have 3 plus 2i over 4 plus 3i, then multiply by 4 minus 3i and 4 minus 3i. Okay, so 3 times 4 is 12. 3 times minus 3i is minus 9i. 2 times 4 is plus 8i. Then minus 2i times 3i. Now, this is where issue is. This one now we're doing. This is where it is. You have I here that resolves to a minus 1. You have minus and plus here that also result to minus. So you have two minus somewhere. The first minus is 2 times minus 3 is minus 6. I times I is minus 1. That's why you have two minuses. Okay, so we're done with this first one. Now this bottom one will give me only two terms. The complex part will disappear always. If you are doing conjugate and the denominator, the complex part does not disappear, it means you have not done anything. You have made a mistake. Okay, so let's go. 4 times 4 is 16, right? 4 times minus 3i is minus 12i. Then 3i times 4 is plus 12i. And 3i times minus 3i. Again, because of the I that is here and the minus that is here. 3 times minus 3 is minus 9, right? I times I is minus 1. Always break it down. So you don't make mistake. Break it down. There are two things here. 3 and I. So 3 has plus here. 3 has minus here. Plus 3i times minus 3i is minus 9. Sorry. Plus 3 times minus 3 is 9. I times I is minus 1. Always. So that you can see how it's done here. So, okay. So from here, I have 12. Minus 9i. Okay, 9. Let's resolve this. Let's resolve this too. Minus 9i plus 8i will give me minus I. Why? Because minus 9 plus 8 is minus 1. Okay, so this and this will give me plus 6 because minus is plus. Then all over. Now look at where I said these two will resolve themselves. You see, always minus 12i plus 12i will cancel. Because you give me 0. So I have 16, then finally plus 9. Minus is plus 9. So you see that the numerator will give me a scalar, give me just one number without a complex number. So I have this and this, they're the same thing, they are the same, I can transfer them together. 12 and 6 is 18 minus I all over 16 plus 9 will give me 25. So 25. So I can do it like this. 18 over 25 minus 1 over 25i. Where this is the real part, this is the complex part. Understand? Okay. So this is how it is. This is the final answer. Or you can do it like this. 25 will come outside. 1 over 25 will come outside. Then I'll have 18 minus I. Anyway, can go. If you see some your objectives as options, you can pick this one or pick this one. That is, if you see them, anyone that is represented. Okay, so we dive into absolute value or modulus of a complex number. The modulus of z1 is equals to z modulus. Just have this how it's written, z modulus. So what does it mean? It means that you will get that if, for instance, if z1 is equals to a1 plus b1i, therefore z1 modulus is equals to square root of a1 square plus b1 square. This is just modulus. So if, for instance, now you are given z1 is equals to 3 plus 2i, and they say evaluate, you'll be seeing this in your exam, so evaluate, like this. Just simply put, z1 modulus is equals to square root of 3 square plus 2 square. This is 3, this is 2. So 3 square is 9, 2 square is 4, which is equals to square root of what? 13. This is the answer. This is the answer. If you can evaluate 13, but you will get a number. So that's the answer. So before we go, we'll look at working distance in complex numbers. The distance given by 2 points, z1 and z2, in a complex plane is actually given like this. So let me just take this off and write that on the board. Working distance in complex number. Working distances. That's how do we resolve this in complex numbers. Okay. So see, if we have z1 given as a1b plus b1 I, and z2 is equals to a2 plus b2i, and they said find the distance between the 2 points. So distance between the 2 points, is given as square root of a2 minus a1 square plus b2 minus b1 all square. It's a scalar. It's a scalar quantity. Example. So if I have 2 points, okay, let's say find the distance. Let me put it the way it's in the material. Find the distance, okay, between the points z1 and z2. So given that z1 is equals to 3 plus 2i and z2 is equals to 4 plus 3i. Okay, so these are so the distance, actually, distance is equals to big square root like this. Now, what do you know to take? Take the A, this and this. Find the difference, and square it. So 4 minus 3, 4 minus 3, then square, plus, then the complex part, 3 minus 2, then square. 3 minus 2, then square. Very simple, simple enough. Again, distance between these two complex numbers is, you take the real part, 4 and 3. 4 minus 3, you square it, plus imaginary part, 3 minus 2, you square it, then find the square root. So that's all. So what you do now is mathematics. 4 minus 3 is 1 all square, plus 3 minus 2 is 1 again all square. So 1 plus 1 is 2, 1 plus 1 is 2, of course. Then the square root of 2 is the final distance of that vector. So that is it. So that's how you work distances of complex numbers. Of course, you get more and more examples, but feel free to use them, manipulate them. Sometimes you might be asked to find modulus, might asked to find magnitude of vectors. So of course we have the polar form of vectors. The polar form of vectors is actually when you represent vector, complex number in Pythagoras form, in trigonometrical form. So we're going to quickly dive in that and close this lecture. Okay, so it is convenient sometimes to express complex number. For instance, z is equals to a plus b1. So in a different form. So on an Argand diagram, this is an Argand diagram that has a Cartesian plane, two-dimensional. If I have a point P here, for instance, and this is where the origin of P is, point P. So if you check, P on the x-axis is represented by A, and P on the y-axis is B. Let me put the B here. So the angle that this line PO form with this is angle theta. Let's call it angle theta. Okay, so we can actually represent this complex form on an Argand diagram. This is A. A part, that's the real part, is the part that can be measured on the x-axis, and B, the imaginary part that has the imaginary part, is the part that can measure on the y-axis. Now recall that from our Pythagoras theorem that they say this OB, OP, that is called the hypotenuse, let's call it R. So from Pythagoras theorem, we know that R is equals to A squared plus B squared all square roots. We know this one. If at this level you don't know this one, then it means your foundation is really, really weak. So we know this one. And also, again, I can express R in terms of A in terms of theta and R. How? This theta that is here and this A and R, we can deduce a trigonometric ratio from it. If this is theta, the opposite of the adjacent of theta is A. So I have adjacent as A and hypotenuse as R. So the trig ratio that can define theta is cos. Cos theta is A over R. That is adjacent over hypotenuse, right? Exactly. So from here, I can say R is equals to A is equals to R cos theta. Let me call this equation 1. So I'm already expressing this A in terms of this. And B can be expressed with a sine, because B is opposite of this angle and R is hypotenuse of this angle. So actually sine theta is equals to opposite, which is b, over r. And I can have b is equals to r sine theta. This is equation 2. So these two equations came from trig identities, 1 and 2, came from trigonometric ratio. What we're trying to do now is we're trying to use polar form to represent this complex number. This complex number. Polar form. Polar form means just using only angle and the r. This is only angle and the r. Okay, so from here now, we can now say, okay, where are we? We can now say z is equals to, when we see a, we put this one, r cos theta, plus b is r sine theta, I. So this one and this one are the same thing. Why? Because I've replaced a with cos r cos theta, and I've replaced b with r sine theta. So that's what I've done here. Okay. But we know that r is defined as root a b. Okay, let me leave it like this. Let me leave it like this. Okay, so this is how we can use polar form to write out the complex number.